Hello and welcome back to another video on SVM, support vector machines, and credit modeling. And what I'm going to be doing this time is looking at ways of dealing with non-linearity. How you divide the data when you can't just draw a straight line through it. And there's a couple of related approaches to this. One is using high dimensions, and the other is actually using a non-linear divider for the data. So let's run through those. Let's run through those now. So the first one I'm going to be looking at is linear SVM with high dimensions. So in 2 dimensions, we've got the set of points x1m, x2m, ym. So x1m is say EBIT over assets, x2m is say the log of assets over liabilities, and ym is it solvent or is it insolvent? So another way of looking at it is x1m and x2m are the 2 characteristics of firm M, and ym is either 1 or -1, representing, say, solvency or insolvency. But we could map this to 3 dimensions with a third variable, a function of x1m, or a function of x2m, or a function of both of these 2. So look at this example here. If you look at the chart on the right, you'll see there's no way of actually drawing a straight line to divide this data, because that annoying little yellow dot on the right hand side is just a little bit too high to be able to perfectly separate the data. So one of the things you could do is you could have a soft margin. So move away from hard margin SVM to soft margin SVM, which we did a couple of videos ago. An alternative is to slightly redefine the data. So create an extra dimension defining the f of x1m, x2m as just x1m squared. So then the set of points that we've got for each observation is x1m, x2m, x1m squared, and ym. So this data might not be separable in 2 dimensions, but it is separable in 3 dimensions. If we just minimize beta 1 squared, beta 2 squared, and beta 3 squared, subject to ym multiplied by beta 1 x1m plus beta 2 x2m plus beta 3 x1 squared m minus beta 0 is greater than or equal to 1. So if you're doing this, it's pretty straightforward. It's just an extension of the previous spreadsheet that we saw. So now you'll see in column D, we've got something which is simply column B squared, EBIT over assets squared, x1m squared. And we've also got an additional beta there, beta 3. But apart from that, the spreadsheet is exactly the same as the previous spreadsheet. You've got an expression there for normal beta squared, which is looking at betas 1, 2, and 3. And you've got column K, which has a minimum value for any of its items of 1. So that shows that we are actually able to draw a line to divide the data. You don't need to rely on a soft margin. So it's all relatively straightforward. So as I said, beta 2 squared here is column D, but otherwise it's exactly the same as before. Now, you can sometimes look at this higher dimension version of SVM slightly differently, because you consider a slightly different data set, and we've minimized beta 1 squared, beta 2 squared, and beta 3 squared subject to that constraint there. You could say it makes the data linearly separable in 3 dimensions, because you can just use a plane there to separate the data. But another way of looking at it is that it is non-linearly separable in 2 dimensions. And the best separating parabola is beta 0 plus beta 1 x1m plus beta 2 x2m plus beta 3 x1 squared m, which is clearly a parabola. And it's also worth noting that you could carry out a non-linear support vector machine using some sort of non-parametric kernel to wind its way between the points. I mean, there's a risk here that you do end up overfitting the data if you use a kernel which is too exact, and it does get increasingly complex as you move into more and more dimensions with more and more variables. But it's just worth noting that that is also an option. So if we look at that expression that we had before, this is what that parabola looks like. So you can see here that we do have two-dimensional separated data here, but with a parabola, so non-linear, rather than a straight line. And also it's worth noting that if we kind of redefine our data, so on the horizontal axis, instead of just having EBIT over assets, we have beta 1 EBIT over assets plus beta 3 EBIT over assets squared. It actually takes us back to a case where it's linearly separable again. So that is also quite interesting. And in this case, we've got the vertical here as beta 2 x2 n. So you can see there that if you move to high dimensions or you use a non-linear expression to try to separate the data, you can still carry out SVM even if you can't just take out a ruler and plot a straight line or hold the ruler as a plane between your data points. But as the number of dimensions increases, as the complexity of the data increases, the computing power required to do this gets increasingly difficult. So what you can sometimes resort to try to make things a little bit more straightforward is something called the kernel trick. Now, this is something which I mentioned before when I was looking at the Lagrangian approach, because you've got to understand the Lagrangian approach to understand how the kernel trick works, to understand some of the maths behind it. And it is quite involved in terms of the understanding of SVMs, but if you're doing real-world SVM, it's something which you probably need to bear in mind to get the most out of this approach. So next time, that's what I'll be looking at, the kernel trick.